Welcome to Pharma Drama, the channel where we look at the science of healthcare and healthcare products. Today we're going to look at the science of a very common dosage form, suspensions. You might think they're simply drug particles suspended in water, but in fact there's much more going on to ensure the patient gets the right dose every time, even if the product has been kept on a shelf for several years. So, get yourself a drink. I've got I won't keep you in suspense, coffee, and let's make a start. Suspensions are one of the oldest types of dosage form, and in simple terms consist of drug particles suspended in water. We call the particles the dispersed phase because, well, they're dispersed, and the water the continuous phase. They're a very good formulation choice for people who have trouble swallowing, particularly children, and you'll often find suspensions are fruit flavoured for that reason. For instance, Calpol, beloved of parents whose children can't sleep, is a suspension of paracetamol in water with a strawberry flavour, while Nurofen for children is a suspension of ibuprofen in water with either a strawberry or orange flavour. Suspensions are also a very good choice for materials that won't dissolve in water, minerals or inorganic salts for instance. So, products like calamine lotion and magnesium trisilicate mixture are suspensions. They are very good for delivering drugs that have poor solubility, because the powder will have a large surface area, and they can be easily taste masked for drugs that taste horrible. I should note here also that suspensions can be used for multiple routes of administration. They can be swallowed, of course, for oral delivery, but they can be applied topically or be formulated for the eye. We call those ophthalmic suspensions. Now, what do we need to worry about when formulating a suspension? Are they simply drug particles suspended in water, as I said just now? No. Here is the patient information leaflet for Calpol. Information leaflets are very interesting because they contain, well, information. In particular, they tell you what's in the product. Here we can see the top ingredient is not paracetamol, but is in fact sucrose. Well, it is for children. After that, we see sorbitol, glycerol and polysorbate 80. Sorbitol is a sugar alcohol that tastes sweet and can act as a thickener. Glycerol can also act as a thickener, and polysorbate 80 is an emulsifier. Why would a simple suspension contain these excipients? Principally because suspensions are not actually that simple. The first thing we must consider when formulating a suspension is the size of the powder particles. You might not think that that would matter much, but actually your mouth is very sensitive to particle size. And if we make a suspension with powder particles that are too large, it will feel very gritty in the mouth. How small do we need to make the particles to prevent the grittiness, I hear you ask? Amazingly, they need to be around 5 micrometers or less. That is very small. To give you some idea of scale, a strand of human hair is around 100 micrometers thick. So we need particles that are 20 times smaller than the thickness of hair. It's quite difficult to make particles that small. We either need to grow them as crystals and stop the crystallization when they get to the right size, or more commonly start with larger crystalline particles and reduce them in size by milling. Either way, we need to take a lot of care in getting the particle size just right. If the particle's very small, less than 1 micrometer in diameter, or 1/100th the width of a human hair, we call the suspension colloidal, and if the particles are larger than 1 micrometer, we call the suspension coarse. Another thing we need to remember about suspensions is that no matter how small they are, the particles will eventually begin to settle at the bottom of the bottle under gravity. This will form a sediment. The rate of settling of particles in a suspension is governed by Stoke's law. It looks rather complicated, but it really just contains some simple factors. the diameter of the particles, the viscosity of the continuous phase, the force of gravity, and the densities of the disperse and continuous phases. It says that as the size or density of the particles increases, they will settle faster, and as the viscosity or density of the continuous phase increases, they will settle slower. It also says if we make suspensions on the moon, the particles will settle slower. But let's not go there, literally or metaphorically. Why does settling of particles matter? Well, imagine for a moment what happens when a patient wants to take a dose of medicine, that is a suspension. First, they will pick up the bottle and shake it, which will have the effect of uniformly distributing the particles throughout the bottle. That's a good thing, because if the particles were not uniformly distributed, then the patient would not get the right dose. The dose will be too low when the product is new and will gradually get too high as the product is used up. This is because the particles can only sediment, so there will always be a greater concentration of them towards the bottom of the bottle if not shaken properly. Then they will pour a dose or drink from the bottle. Ideally, we don't want the particles to start to settle between shaking and pouring because, as we just noted, we don't want the wrong dose. Now, how do we ensure that? Well, because we have a very small particle size, Stoke's law says the rate of settling will be slow. So that's good. Is that all we need to worry about when formulating a suspension? Unfortunately not. Things are never that simple. To understand why, we also need to think about what the product will look like after a period of storage when the particles have finished settling and formed a sediment. When a suspension contains small particles that settle slowly, the sediment that forms will be small and quite dense. Think of it in terms of playing a game of Tetris. When the rate the pieces fall is slow, you have lots of time to orient them and pack them together, leaving no space between them. As you might imagine, a dense, well-packed sediment will be quite hard to redisperse on shaking. The consumer will have to shake the bottle very hard and may not even be able to redisperse the particles completely. And then we are back to variable dose and gritty mouthfeel. To have a sediment that is easy to redisperse, we want it not well packed, with lots of space between the particles. How might we achieve that? Well, to return to my Tetris example, imagine what happens when the pieces fall much faster. We can't orient the pieces fast enough to make sure they pack perfectly, and so we end up with gaps at the bottom of the game. The same thing happens with suspensions. The faster the particles settle, the less well packed the sediment will be, and the easier it will be to redisperse. How then do we get the particles to settle faster? We can look at Stoke's law and see what we can vary. Can you see what we might do? Yeah. We could change the force of gravity, but that's really tough, so we're not going to do that. We could lower the viscosity of the continuous phase, but generally suspensions are made in water, and that already has a pretty low viscosity. We can't change the density of the particles, so that only leaves one option, which is to make them bigger. But hang on, didn't we say that bigger particles would make the suspension feel gritty? We did! So what can we do? The answer is we do something rather clever, which is we add something to the suspension, an excipient, that causes the particles to bind weakly together. The excipient can be a polymer, the long chains of which wrap around the particles and entangle them together, or a mixture of electrolytes, which add surface charges to the particles, causing them to clump together with electrostatic charges. Clumps of particles loosely bound like this are called flocks, and the excipients that cause flocks to form are called flocculating agents. By making flocks, we create larger particles that will settle more quickly, and as an added bonus, because they are weakly bound together, they already have space between them, so they form a very easy to redisperse sediment. Now, and finally, you'll be pleased to know, You might say to me, hang on a minute, Simon. You said we wanted particles to settle slowly to ensure a uniform dose, but fast to ensure an easy to redisperse sediment. Aren't these things in opposition to each other? And I would say, well done for still watching, because it really helps the channel's metrics. And yes, you're absolutely right. When we formulate a good pharmaceutical suspension, we have to strike a balance of factors. We want the suspension to be easy to shake and disperse the particles, but we want the particles to settle fast to make sure a hard sediment doesn't form. A really good way of ensuring this is to make sure the particles are flocculated, so they settle fast into a loosely bound sediment. But if settling is too fast to ensure uniformity of dose, we can increase the viscosity of the continuous phase slightly by adding a viscosity enhancer or a thickener. As always with suspensions, we are aiming for a good balance between competing factors. Right, that's all we need to know about suspensions. They contain drug particles suspended in, usually water, and are really good dosage form for those who have trouble swallowing, for drugs that dissolve slowly, for taste masking, and or for delivery to the skin or eye. The ideal suspension is hard to formulate, however, because we have two competing factors to balance: ease of redispersion and the need for dose uniformity. And we manage that by creating particle flocks and by slightly increasing the viscosity of the continuous phase. I hope you found that useful. If you did, please hit the like button, subscribe if you haven't already, and please tell your friends about the channel. All of that really helps. Otherwise, thank you so much for watching, and I'll see you again soon.